Welcome to the lecture on interest factors for continuous compounding. So, we will discuss first how the continuous compounding is defined, and then we will also derive the expressions for the continuous compounding cases. Before that, let us see that how the compounding is changed when we have seen that when the number of periods per year is changing. In that case, in the earlier lecture, we have seen that when we are changing these compounding periods per year, number of periods per year, in that case the effective interest rate per period will be changing, not per period for any particular time. So, per period certainly it will be similar. So, we can have the example from here. Basically, we can have the table which tells us about the comparison of interest rates for 12% nominal rate of interest, and how when we change the compounding frequency, then how the annual interest rate will be changing. So, if you look at the first case of compounding frequency annually, it means the number of period for which the compounding is done per year will be 1, and effective interest rate per period will be 12. So, certainly it is annual interest rate becomes 12%. So, we call it as 12% compounded annually. When we talk about the 12% compounded semi-annually, we discussed it, that then your period becomes number of periods for which the compounding is carried out is 2, and per period effective interest rate, because your period for which the interest rate is compounded is 6 months now, and for 6 months the effective interest rate will be 6%. But if you calculate the effective interest rate for the whole year, it will be different. So, it will be 1.06 multiplied by 106, and then that will be subtracted, so 100, that number minus 100. So, that will be the interest. So, basically that becomes 12.36. Then if you do it quarterly, so you are doing the compounding 4 times, and effective interest rate per period will be 3%, because in that case, so 3 into 4 is 12, and in that case annual interest rate, if you compute again 1 plus r by m raised to the power lm minus 1. So, lm is normally taken as c also, that was shown. So, that minus 1 becomes 12.55. Then go to monthly. In monthly basis, your number of periods per year becomes 12. Effective interest rate for 1 month will be 12 by 12, that is 1, and in that case your annual interest rate effective value will be 12.68%. If you compute further weekly, then you have 52 times compounding. So, compounding number of periods for which the compounding is done is 1 week. So, it will be 52 times, and for every week you have a 0.23%. So, 12 by 52. So, that way you get this 0.23, and annual interest rate if you compute it will be 12.73%. Now, if you do the daily basis, the same thing comes out. So, you are doing 365 times, and your effective interest rate every day will be 0.0328%, and your annual interest rate computed will be 12.747% or so. So, that is how you see that your annual interest rates will be varying. Now, another case is which is very much practiced by the financial institutions and banks is the continuous compounding, and for that basically we are going to define that what is continuous compounding. Continuous compounding is that case when compounding is done infinite times, infinite number of times, during the year. So, basically the number of interest periods per year is, so that is approaching infinity, and that is why the length of this compounding period will be approaching 0. Now, so in these cases your value of this effective interest rate per annum will be to be computed. Now, that can be computed by using that formula again. So, what we have seen that effective annual interest rate IA, we know that in this case you have 1 plus r by m raised to the power L m and minus 1, and L is 1 year. So, since you are doing annually, so for annual case, for annual period, L will be 1. Now, in this case 1 plus r by m raised to the power L m, so it will be 1 minus 1. Now, in this case the thing is your period, that is this m is going to be infinity. So, you are taking m tending towards infinity that way. So, in that case if you try to define, now what we see, you can recall that expression that limit m tends to 0 and 1 plus r by m, and it is raised to the power m by r, it is defined as the exponential function, that is e, and this e is nothing but 2.7182, and then you have further the number. So, this can further be written as limit m tends to infinity, and then you will be writing 1 plus r by m, then m by r, and then raised to the power r. So, this can be written as 1 plus r by m raised to the power m. So, and then minus 1. So, we know that this this quantity becomes e. So, it will be e raised to the power r minus 1. So, as this is becoming e, so you will have e raised to the power r minus 1. So, the effective interest rate which is computed in such a cases will be e raised to the power r minus 1. So, when your nominal interest rate is defined, then you can have these value of this effective interest rate for the continuous compounding case e raised to the power r minus 1. Now, what happens that when we are dealing with such situations where you have to compute these interest factors for all these cases, in that case you have to use this e raised to the power r minus 1 as the effective interest rate per year. And if you look at ER, so basically ER becomes 1 plus IA. So, most of the times you are using this 1 plus IA, and that will be replaced with now ER in all those situations when we are dealing with these continuous compounding cases. Now, if you are dealing with that continuous compounding formulas, we have to we are, I think, conversant with all these terminologies which we have used earlier, that is P will be your present amount. So, that is a present principal. So, you will have P, then that is your present principal, then you have F as the future sum, so future value, or FV sometimes we also call it as. Then you have you have all as R. Here you will have a term known as R, that is your nominal interest rate. So, R will be your nominal interest rate, nominal annual interest rate. Then you will have N. Now, N is the number of annual periods. Then you may also come across the term known as A, what we have discussed earlier. So, you will have all these factors like P by F Rn, and then f by p Rn, or a by p Rn, or p by a Rn, or different, based on all these different terminologies, different factors, you will have different names, and we can have the expression for that. So, A basically is the a single payment which is in a series of n equal payments and made at the end of each of the annual period. So, that is what we call it as A. So, that is we also call it as annuities or so. So, now we will go one by one to the different factors. First of the factor is the single payment compound amount factor. Now, this we are discussing for the case of continuous compounding. Now, in the case of for annual compounding, if you look at, what we see is, for annual compounding, when we do, we are telling that f equal to p into 1 plus r raised to the power n. So, that is what the formula will be applied, and factor will be 1 plus r raised to the power n if there is annual compounding. If it is for semi annual compounding, then in that case we have seen that your interest becomes r by 2, so 1 plus r by m and then l into m. So, if you are doing 2 times, then in that case f will be p into 1 plus r by 2, and then you will have 2n, because what happens that your time period is 1 and your this is becoming 2. So, 1 into 2 and then raised to the power n. So, that is how your r by 2 and raised to the power 2n. So, similarly, if you go for, suppose you go for monthly compounding, then you know that it will be f equal to p into 1 plus r by 12 raised to the power 12 n. So, that is how you go in those cases. So, if you have, so it means in general you can write that if there are m compounding periods, per year, in that case your equation becomes f equal to p into 1 plus r by m and then mn. Now, when we talk about the infinite times of compounding, in that case your m becomes m is tending towards infinity. So, that is the case of continuous compounding. So, when we talk about the continuous compounding case, in that case, so for continuous compounding, what will happen? Now, for continuous compounding, what will happen, that the same thing, you will have f equal to p, and then you will have limit, and then this m will be tending towards infinity, and you have 1 plus r by m raised to the power mn. So, that is what your this expression for the single payment compound amount factor will look like. Now, what we can have is that we can write again that this factor as one limit m tending towards infinity, 1 plus r by m raised to the power m by r, that is e, and then raised to the power r n. So, you can see that this f will be basically, we can further write p into then you have limit m tending towards infinity, and it will be 1 plus r by m, and you have mn. So, you write down m by r, and this whole raised to the power, it will be rn. So, that this r and r cancels and it becomes mn. So, you had mn earlier, this mn was there. So, this mn is still intact. So, that is how you call it as for this case. Now, in this case this will be basically this quantity will become E. So, it will be P into then this will be e raised to the power r n. So, what we see that this value will be p into r n. So, f will be equal to p raised to the power r n. Now, this factor, so the factor single payment compound amount factor is normally f by p r n, and this basically is nothing but it is e raised to the power r n. So, this is in the earlier case you had this one as 1 plus I raised to the power n minus 1 n basically not 1 minus 1, and in this case as we discussed that 1 plus I basically is e raised to the power r, and then since it is raised to the power n, so it will be e raised to the power r n, and this is this factor is nothing but single payment compound amount factor for continuous compounding case. For continuous compounding interest. So, that is how we try to define the case of the factor of the single payment compound amount factor in the case of continuous compounding. Now, we can see this calculation of the factor for the single payment present worth factor. Now, as we discussed that this how this came out. So, we have already I told you that we have seen that 1 plus I will be e raised to the power r. So, that is how 1 plus I raised to the power n is there in a normal case. So, this raised to the power so e r raised to the power n. So, e raised to the power r. So, that e r n. So, that is how it becomes. Now, we will see the next factor, that is single payment present worth factor. Now, this single payment present worth factor as we know that this is p by f and r n it will be, and it will be the reciprocal of the single payment compound amount factor. And if you look at that, so basically it should be p equal to f into that factor p by f r n. So, it will be p, so it will be basically reciprocal of the single payment compound amount factor, and that is why it will be 1 by e raised to the power r n. So, you can write f into e raised to the power minus r n. So, basically 1 by e r n or e raised to the power minus r n is the single payment present worth factor for continuous compounding interest. Now, we will further move. We will move to the equal payment series factor, and then we will calculate for equal payment series present worth factor. So, we are interested to know the factor p by a r n. Now, in this case what is there is that you are trying to have a factor which should be multiplied with a, so that it gives you the value of p. Now, the thing is that in this case if you see, so you will have p, and that value will be a will be there. So, you will have a all that going on. Now, in this case for such cases you can see that the P is now this A now for you know and you have this payment of A. If you look at now, if you try to find the expression for P, now if you find this total present worth value for these and that will be the sum of the individual present worth values for these deposits. Now this will be for the A which is occurring at 1. So, it will be e raised to the power minus r. So, it will be basically you know its present worth will be in the normal case it should have been 1 by 1 plus I. So, this will be 1 by 1 plus I and 2 times. So, that way in this case 1 plus I is nothing but e raised to the power r. Now, its reciprocal will be e raised to the power minus r. So, this A will have e minus r. Similarly, you know then further for the next A it will be e then minus r2 then e minus r3. So, it will be going and you have n payments. So, e and e raised to the power minus r n. So, that is how it goes. So, this series basically is a geometric series. You can have the A e raised to the power minus r as the common one. So, you will get 1 plus e raised to the power minus r. So, this way it will go up to e raised to the power minus r into n minus 1. So, this becomes a geometric series, and if you take its you know sum. So, it will be, we know that for geometric series it has the first term as 1 and the common ratio is e raised to the power minus r. So, 1 by e raised to the power r. So, that is basically going to be less than 1. So, it will be 1 minus r n upon 1 minus r and first term is 1 itself. So, it will be 1 minus r raised to the power n. So, you have n terms. So, e raised to the power minus r n divided by 1 minus r, and r is nothing but e raised to the power minus r, common ratio. So, this term will be again seen. So, it is so you can further see it will be a into 1 minus e raised to the power minus r n, and then this e minus r will be going at the denominator as e r, and e r will be multiplied with this term. So, this will be e r and minus this will be 1. So, now what you see that when there is a continuous compounding, in that case you have this e raised to the power r minus 1 will be at the bottom, and this factor. Now, this factor is, so this factor is used to find the present worth provided A is given, and this factor multiplied with A will give you the present worth. So, that is why it is known as equal payment series present worth factor, that is you know this is P by A R n, and this is equal payment series present worth factor, you know and in that case you have for the continuous compounding interest. So, that is how this factor will be denoted as you know P by A R n. So, you may have other you know equal payment series factors, and if you have equal payment series capital recovery factor, so equal payment series capital recovery factor will be the reciprocal of the equal payment series present worth factor, and this is for you know for continuous compounding, and for this you know it will be reciprocal of the equal payment series present worth factor, and it will be again A by P R n and you can have it. So, earlier you had you know, e raised to the power 1 minus e raised to the power r n and minus r n divided by e r minus 1. Now, it will be you know, e raised to the power r minus 1 by 1 minus e raised to the power minus r n. So, this factor when multiplied with p, that will give you the value of the, you know, a. So, that is your equal payment series value. Then you may have another factor, that is equal payment series sinking fund factor. So, you know, this is again we are to do for continuous compounding of interest. Now, in this case what we do is that we know that this is a by f r n. So, this factor when multiplied with f will give you the a value. So, it is nothing but a by f r n. So, this is the you know, equal payment series sinking fund factor, and we had equal payment series compound amount factor, that is f by a I n. Now, if you look at a and p, what we have seen is that a is nothing but we know. So, for how to calculate this, for this you can have, we know that a will be p into e r minus 1 and divided by 1 minus e raised to the power minus r n, and then we also know that p is nothing but you know, f into e raised to the power minus r n. So, that we have already got this factor. So, it will be multiplied with e r minus 1 and divided by 1 minus e raised to the power minus r n. So, you will get it this value as f into this e raised to the power r n will go at the bottom. So, you will have e raised to the power r minus 1 divided by e raised to the power r n and then minus 1. So, this factor e raised to the power r minus 1 divided by e raised to the power r n minus 1, this factor is basically you know, known as equal payment series sinking fund factor, and for continuous compounding. So, that is how we define for the continuous compounding cases. Then as we know that equal payment series you know, compound amount factor, and that too for the continuous compounding cases. Now, for this as you know that this will be reciprocal of the equal payment series sinking fund factor, and this factor will be multiplied with a to give you the present compound amount. So, it will be reciprocal of the factor which has been found out, and it will be e raised to the power r n minus 1 divided by e raised to the power r minus 1. So, this factor is basically denoted as f by a r n. So, this is the nominal interest rate r, and n is you know, the compounding periods, and that is your this factor e raised to the power r n minus 1 by e r minus 1. So, that gives you the value of you know, the equal payment series compound amount factor for continuous compounding. We can have even for the you know, gradient series factors, and for example, if you look for the uniform gradient series factor. So, uniform gradient series factor, if you look at here, you get a between a and g. So, what we see is that we can see have a equal to g into 1 by e r minus 1 minus n upon e raised to the power r n minus 1. So, you can you know, see the value of 1 plus I in those cases, and you can try to replace it, and what you see 1 by I, basically what we see there 1 by I minus n by you know, 1 plus I, n minus 1. So, that way it becomes 1 by E r minus 1. So, like that. So, basically this factor basically will be the uniform gradient series factor for continuous compounding. So, in such cases what we see that you can have this. You can also calculate this geometric gradient series factors also there also. Accordingly, when whatever expressions you have, accordingly you can have the values being replaced. 1 plus I may be replaced with e raised to the power r. So, you can have that expression for the uniform gradient series factors. So, all these factors will be used for calculating the value of the value of f or a or p or so, and use of these formulas are basically suggested to be for the future applications. Thank you very much.